Hello friends, in our previous discussion we have been discussing the BJT amplifiers and their operation. From now onwards we shall start discussing the power amplifiers. Power amplifiers are large signal amplifiers. This generally means that a much larger portion of the load line is used during signal operation than in a small signal amplifier. During these lectures, we will cover 4 classes of power amplifiers, namely class A, class B, class AB and class C. These amplifier classifications are based on the percentage of the input cycle for which the amplifier operates in its linear region. Each class has a unique circuit configuration because of the way it must be operated. The emphasis is on power amplification. Power amplifiers are normally used as the final stage of a communication receiver or transmitter to provide signal power to speakers or to a transmitting antenna. BJTs are used to illustrate power amplifier principles. The class A power amplifier. When an amplifier is biased such that it always operates in the linear region where the output signal is an amplified replica of the input signal, it is a class A amplifier. Discussion on amplifiers in the previous lectures applies to class A operation. Power amplifiers are those amplifiers that have the objective of delivering power to load. This means that components must be considered in terms of their ability to dissipate heat. After completing this section, you should be able to explain and analyze the operation of class A amplifiers, discuss transistor heat dissipation, describe the purpose of a heat sink and finally define and determine the efficiency of a power amplifier. Class A amplifier operation. In a small signal amplifier, the AC signal moves over a small percentage of the total AC load line. When the output signal is larger and approaches the limits of the AC load line, the amplifier is a large signal type. Both large signal and small signal amplifiers are considered to be class A if they operate in the linear region at all times as illustrated in figure here. Class A power amplifiers are large signal amplifiers with the objective of providing power rather than voltage to a load. As a rule of thumb, an amplifier may be considered to be a power amplifier if it is rated for more than 1 watt and it is necessary to consider the problem of heat dissipation in components. Heat dissipation. Power transistors and other power devices must dissipate a large amount of internally generated heat. For BJT power transistors, the collector terminal is the critical junction. For this reason, the transistor's case is always connected to the collector terminal. The case of all power transistors is designed to provide large contact area between it and an external heat sink. Heat from the transistor flows through the case to the heat sink and then dissipates in the surrounding air. Heat sinks vary in size, number of fins and types of materials. Their size depends on the heat dissipation requirement and the maximum ambient temperature in which the transistor is to operate. In high power applications like a few hundred watts, a cooling fan may be necessary. Centered Q point. Recall that the DC and AC load lines intersect at the Q point. When the Q point is at the center of the AC load line, a maximum class A signal can be obtained. You can see this concept by examining the graph of the load line for a given amplifier as shown in the figure. This graph shows the AC load line with the Q point at its center. The collector current can vary from its Q point value up to its saturation value, that is IC saturation, and down to its cutoff value of 0. Likewise, the collector to emitter voltage can swing from its Q point value of VCEQ up to its cutoff value of VCE cutoff and down to its saturation value of near 0. The peak value of the collector current equals ICQ and the peak value of the collector to emitter voltage equals VCEQ in this case. The signal is the maximum that can be obtained from the class A amplifier. Actually, the output cannot quite reach saturation or cutoff, so the practical maximum is slightly less. If the Q point is not centered on the AC load line, the output signal is limited. Figure here shows an AC load line with the Q point moved away from the center towards cutoff. The output variation is limited by the cutoff in this case. The collector current can only swing down to near 0 and an equal amount above ICQ. The collector to emitter voltage can only swing up to its cutoff value and an equal amount below VCEQ. If the amplifier is driven any further than this, it will clip at cutoff. Figure here shows an AC load line with the Q point moved away from the center towards saturation. In this case, the output variation is limited by saturation. The collector current can only swing up to near saturation and an equal amount below ICQ. The collector to emitter voltage can only swing down to its saturation value and an equal amount above VCEQ. If the amplifier is driven any further, it will clip at saturation as shown in part B of figure. Power gain. AP is equal to PL over PN, where AP is the power gain, PL is signal power delivered to the load, and Pn is signal power delivered to the amplifier. The power gain can be computed by any of the several formulas depending on what is known. Frequently, the easiest way to obtain power gain is from input resistance, load resistance, and voltage gain. To see how this is done, recall that power can be expressed in terms of voltage and resistance as P is equal to V square over R. For AC power, the voltage is expressed as RMS. The output voltage delivers to the load and is given by this equation where PL is equal to V square L over RL. The input power delivered to the amplifier is Pin is equal to V square N over Rn. By substituting the values of PL and Pn in power gain equation, we get AP is equal to V square L over V square N into Rn over RL. Since VL over Vn is equal to AV, AP is equal to A square V into Rn over RL. This equation shows that the power gain of an amplifier is the voltage gain squared times the ratio of the input resistance to the output load resistance. The formula can be applied to any amplifier. For example, assume a common collector amplifier has an input resistance of 5 kilo ohms and a load resistance of 100 ohms. Since a common collector amplifier has a voltage gain of approximately 1 and substituting the values in the equation, the power gain comes out to be 1 square into 5 kilo ohms over 100 ohms is equal to 50. For a CC amplifier, AP is just the ratio of the input resistance to the output load resistance. DC quiescent power. The power dissipation of a transistor with no signal input is the product of its Q point current and voltage, that is PdQ is equal to ICQ into VCEQ. The only way a class A power amplifier can supply power to a load is to maintain a quiescent current that is at least as large as the peak current requirement for the load current. A signal will not increase the power dissipation by the transistor, but actually causes less total power to be dissipated. The DC quiescent power given in equation is the maximum power that a class A amplifier must handle. The transistor's power ratings must exceed this value. Output power. In general, the output signal power is the product of the RMS load current and the RMS load voltage. The maximum unclipped AC signal occurs when the Q point is centered on the AC load line. For a CE amplifier with a center Q point, the maximum peak voltage swing is Vc maximum is equal to ICQ into RC. The RMS value is 0.707 Vc maximum. The maximum peak swing is given by this equation. IC maximum is equal to VCEQ over RC. The RMS value is 0.707 IC maximum. To find the maximum signal power output, use the RMS values of maximum current and voltage. The maximum power out from a class A amplifier is P out maximum is equal to 0.707 Vc into 0.707 IC, and P out maximum comes out to be 0.5 ICQ into VCEQ. Efficiency. The efficiency of any amplifier is the ratio of the output signal power supplied to a load to the total power from the DC supply. The maximum output signal power that can be obtained is given by this equation, where P out maximum is equal to 0.5 ICQ into VCEQ. The average power supply current ICC is equal to ICQ and the supply voltage is at least 2 VCEQ. Therefore, the total DC power is PDC is equal to ICC into VCC and is equal to 2 ICQ into VCEQ. The maximum efficiency eta maximum of a capacitively coupled class A amplifier is given by this equation, where eta maximum is equal to P out over PDC. Substituting the values, we get efficiency equal to 0.25. The maximum efficiency of a capacitively coupled class A amplifier cannot be higher than 0.25 or 25%, and in practice is usually considerably less, say about 10%. Although the efficiency can be made higher by transformer coupling the signal to the load, there are drawbacks to transformer coupling. These drawbacks include the size and cost of transformers, as well as potential distortion problems when the transformer core begins to saturate. In general, the low efficiency of class A amplifiers limits their usefulness to small power applications that require usually less than 1 watt. When an amplifier is biased at cutoff so that it operates in the linear region for 180 degrees of the input cycle and is in cutoff for 180 degrees, it is a class B amplifier. Class AB amplifiers are biased to conduct for slightly more than 180 degrees. The primary advantage of a class B or class AB amplifier over a class A amplifier is that either one is more efficient than a class A amplifier. You can get more output power for a given amount of input power. A disadvantage of class B or class AB is that it is more difficult to implement the circuit in order to get a linear reproduction of the input waveform. The term push-pull refers to a common type of class B or class AB amplifier circuit in which two transistors are used on alternating half cycles to reproduce the input waveform at the output. After completing this section, you should be able to explain and analyze the operation of class B and class AB amplifiers. Describe class B operation. Discuss Q point location. Describe class B push-pull operation. Discuss transformer coupling. Explain complementary symmetry transistors. Explain crossover distortion. Class B operation. The class B operation is illustrated in figure here. Here, the output waveform is shown relative to the input in terms of time. The class B amplifier is biased at the cutoff point so that ICQ is equal to 0 and VCEQ is equal to VCE cutoff. As illustrated in the figure, it is brought out of cutoff and operates in its linear region when the input signal drives the transistor into conduction. This is an emitter follower circuit where the output is not a replica of the input. As shown, the circuit conducts only for the positive half of the cycle. To amplify the entire cycle, it is necessary to add a second class B amplifier that operates on the negative half of the cycle. The combination of two class B amplifiers working together is called push-pull operation. There are two common approaches for using push-pull amplifiers to reproduce the entire waveform. The first approach uses transformer coupling. The second uses two complementary symmetry transistors. These are a matching pair of NPN or PNP BJTs. Transformer coupling. Transformer coupling is illustrated in figure here. The input transformer has a center tapped secondary that is connected to ground, producing phase inversion of one side with respect to the other. The input transformer thus converts the input signal to two out of phase signals for the transistors. Notice that both transistors are NPN types. Because of the signal inversion, Q1 will conduct on the positive part of the cycle and Q2 will conduct on the negative part. The output transformer combines the signals by permitting current in both directions, even though one transistor is always cut off. The positive power supply signal is connected to the center tap of the output transformer. Complementary symmetry. Transistors shown in this figure are one of the most popular types of push-pull class B amplifiers using two emitter followers and both positive and negative power supplies. This is a complementary amplifier because one emitter follower uses an NPN transistor and the other a PNP, which conducts on opposite alternations of the input cycle. Notice that there is no DC base bias voltage, thus only the signal voltage drives the transistors into conduction. Transistor Q1 conducts during the positive half of the input cycle and Q2 conducts during the negative half. When the DC base voltage is 0, both transistors are off and the input voltage must exceed VBE before a transistor conducts. Because of this, as shown in the waveform here, there is a time interval between the positive and negative alternations of the input when neither transistor is conducting. The resulting distortion in the output waveform is called crossover distortion. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. In today's lecture, we explained and analyzed the operation of class A, class B and class AB amplifiers, described the purpose of a heat sink, described the relationship of the DC and AC load lines with the Q point, discussed and determined output signal power, defined and determined the efficiency of a power amplifier, discussed transformer coupling, explained complementary symmetry transistor, explained crossover distortion. So that is it for today. See you in the next lecture where we shall be discussing more about power amplifiers.